diving equipment and chamber disinfection. So thank you very much, Francois. Also a very relevant topic for us to discuss during this, especially during this time of COVID, and sort of revisiting all our disinfection and hygiene protocols. Thanks.
So as Cecilia said, this has become a really relevant topic for us, and I'm going to be talking about this in context of both diving and hyperbaric, most hyperbaric and diving equipment, because it pretty much applies across the board. And COVID has given us kind of a real, I wouldn't say a wake-up call, but has essentially told us that we don't know everything, and this is something new. I mean, it's been a pandemic that's shaken the world. How does this affect us in terms of our activities? And it's, I don't know whether it'll ever pass, but we need to look beyond that, because we're going to be taking some of these lessons forward as we progress. Okay, so I'm going to start off by saying infection control is more than disinfection, because very often infection control is certainly, in our operational terms, we think it's just simply disinfection after the activity or the treatment. But, and I'm going to talk on, just mention a couple of things that Jack will have to correct me if I miss something, and I feel a little bit intimidated even showing the slide. But in essence, the way we would do infection control, certainly in our context, is to obviously know what it is that we're concerned about. And we've gone through periods of time where tuberculosis and other things have been a concern in hyperbaric environments. So, we've got some idea of reacting to the prevalent pathogens. But we try to minimize that first, so avoiding doing things we don't need to do, so contact and touching and so on. Isolating the area and limiting the access to that area is, a real great step in preventing the spread of any pathogens. But what we really want to do ultimately is disinfecting and get rid of them as best we can. And to do that, we need to know how that pathogen is going to last in terms of time, and how any disinfection we do is going to kill that, or at least inactivate it. Cleaning is an essential part of that. So before one disinfects, you need to clean, because if you have gross amounts of contamination there, the disinfectant is simply not going to get to the pathogen. And then disposing of that contaminated waste product doesn't help just throwing it into the trash can or the dustbin in the hyperbaric unit or wherever you're working. And then monitoring to make sure that we're actually doing the infection control is actually being practiced correctly. And those are essentially the parts that I've tried to explain to folks, that it's not just about the disinfectant. And the second thing I want to do is just define some of the terms that we will talk about in terms of selecting disinfectants. So disinfection is one of 4 or 5 parts of the overall killing the bugs. We have sterilization, which is the ideal, where we kill all of these microorganisms, and this is very traditional. We've used autoclave, steam, heat. We can use chemicals. We're using certain gases are very effective, plasma and irradiation. Some of our new medical devices are actually irradiated before they get implanted to make sure there's nothing live or semi-live in the case of a virus. Disinfection is what I'm going to be primarily talking about. So you need to know it doesn't kill everything. And there's some of the pathogens that just are going to be resilient to any form of disinfection. We just need to know what they are. And the way we will get rid of those is through cleaning and obviously preventing them getting there in the first place. I want you to understand that to disinfect something, it only works on hard and non-porous surfaces, with very, very, very rare exception. And I say rare, it's more on the sterilization side than disinfection. And we do this, most of us do through chemical processes or a combination of chemistry and heating. And UV light is a relatively new one to what we're doing, but it has its limitations. Then the term that is actually describing most of what we do is sanitization. And that's, again, reducing the pathogen count, but it doesn't get to everything. The benefit of this, or what happens with some disinfectants, is they're only sanitized, is we can start to deal with porous materials. We treat them exactly the same as we treat any disinfectant process, but we have to understand that we're going to be getting up to 90-95% pathogen kill, but never up to 100%. And then the really important step in this is cleaning, and I can't hammer this home hard enough. It's exactly the same as we do in oxygen cleaning for equipment. Get rid of the gross contamination, and then your disinfectant is going to be far more effective at doing what it needs to do. And then the last term we use is sanitation, which is getting rid of that waste material that it doesn't then cause the spread of the pathogen, the bacteria again. So those are the terms, and certainly between sterilization, disinfection, sanitization, those are often mixed up, and people don't realize that they're not the same thing. Okay, so it's more than just disinfection or complying with the various acts and regulations in South Africa. And as Jack tried to explain to me, it's very complicated and very difficult to come to terms with all of this. Then we have our Department of Health DTI requirements, DTI mostly for importing of stuff, but these all give guidance, but certainly they don't address anything to do with that magic word hyperbaric. And very often they don't do a decent job at explaining how to do it effectively. These are mostly requirements that have to be met, requirements before something can be used, rather than how effective is it. We have in the US, I'm going to bring a couple of US things in because they are really useful. While they don't perhaps apply, they will give you the guidance, give us the guidance that we need. Are we on the right track with that particular product? Now, I will demonstrate some of this to you. Then we have the safety data sheet, or the old days, the material data sheet that comes with all products, gives us some guidance, doesn't help us in terms of what happens in a hyperbaric chamber, of course. And so whether South Africa approved or not is not really helping us make that decision on our equipment. It says you can use it. It just doesn't say, is it effective on the inside of a dive helmet? Is it effective on the inside of a chamber? And I'll mention some of those reasons for you too. So ultimately, it's the end user that needs to make that decision as to whether it's going to work, not the person trying to sell the product, because they have their limited focus, and the users need to know how they're going to apply it and can it be applied in some cases. So the SARS-CoV-2 virus, we know, is not a particularly strong virus and can be inactivated by most other virucides. So you'd follow pretty much the same process. We need that confidence to know that it's going to address this particular virus. In our conditions, of course, hyperbaric conditions, we've got non-metallic surfaces, porous materials, clothing, and so on, that we know we can't kill all the bugs. We have acrylic windows that are especially sensitive to some of the disinfectants that are pretty effective. The environment is confined, meaning we can't always get to everywhere. And once we've done our disinfection, we put people back in there. And, small amounts of vapor are going to obviously affect people in close proximity. And then the internal configurations, we can't always get to this, some of the places in the hinges and the deck plates, in the door seals. There are areas that are really difficult for us to be able to access. And this applies to both multi-place chambers. We have, one accredited one and several other ones in South Africa, and monoplace chambers. Sometimes monoplace chambers are a little bit easier, but it has more acrylic. So we need, much higher focus on what it is we do. And we shouldn't forget that hospitals have their policies, and one can't fall outside of the policy. And maybe not in South Africa, but I've certainly seen in other countries where the hospital overrules the hyperbaric unit and says, whatever you do, you still need to use this particular disinfectant. We don't trust what you're using, and that's led to damage in hyperbaric facilities. And then we're going to use the same approach for commercial diving equipment. I'm not touching on scuba, recreational scuba. We have solutions for most of what we do in recreational scuba, but equipment that is then being shared or that is being used continuously by occupational people, our concern is occupational workers. If we are now managing them, we are responsible for any infections that they might pick up. And they have a combination of hard surfaces, the inside of the helmet, versus soft and porous surface, the cushions, the wetsuits, and other things that are difficult to disinfect appropriately. So we have the CDC, a South African version, and the US version. And then what that does is it gives us what are the viruses, how effective are they, and what do we need to be targeting? In the US, the EPA, which is the Environmental Protection Agency, registers all pesticides, meaning anything that's able at killing bugs, any microorganisms. However, it focuses primarily on hard surfaces. So it's not going to give us what it is we're looking for in soft surfaces. Now, I have seen disinfectants that are EPA registered, not COVID specific, but they do address products like wetsuits. It specifically mentions wetsuits, but it's not available in the US. It's a Canadian product and doesn't seem to be being exported either. The registration process doesn't obviously address a lot of the materials we would be using. They talk about kitchens and hospital facilities and dairy facilities and various other things. So we have to interpret in the actual application whether the masks or whatever it is we're using are going to be disinfected. And in these registrations, we get the contact time, the dilution, how to apply it, what are the bugs it's going to actually affect. We do have a safety data sheet, but clearly this is very, very rarely specific to anything we're really doing. They won't mention the words diving equipment or hyperbaric or wetsuits or any of that sort of stuff. And it's not the same as the technical data sheet or the product data sheet. If you're lucky enough to find a product with a technical data sheet, you'll get a lot more information about, to help us and make our decisions. But the STS does identify the hazards to people, again, outside of a hyperbaric context. But what are the dangers to people applying it, to people, being subject to it afterwards? What are the flammability requirements? Sometimes something about the materials in terms of corrosion. And it then allows the user to mitigate that by not exposing certain surfaces or providing proper ventilation time between disinfections and so on. Now, I get these questions. We get these questions. And I say I get these questions purely because from you folks, you send me the question, you say, can I use this disinfectant? And it's not an easy answer to give because there are many aspects to this. But I hope in presenting these criteria to you, you'll feel more confident yourselves in making these decisions. Firstly, I want to say that everything we deal with in terms of disinfectant is what's called a pesticide. Because a virus and a bacteria is a pest. So often you're going to see the words pesticide, or when you're looking through the literature, that's the key word where you want to start. And that covers everything we talk about, the disinfectant, the biocide, sporicide, virusicide, fungicide, things that obviously affect those particular pathogens. Sometimes they are antiseptics, meaning it's a disinfectant applied to people rather than to other inanimate objects. But ultimately, we're talking about the pathogen, and we need to make sure that whatever disinfectant we're using is going to affect that pathogen. And the word COVID doesn't appear in many of the products involved. They are catching up now and essentially submitting that their virusicide is going to be effective with the SARS-CoV-2 virus. Okay, so the first question is then to see, is it effective? And the EPA is a great repository for this, but the technical data sheet from the manufacturer of that particular product should tell you which of the products it's effective for and which ones it's not. Because bacteria and funguses or fungi are often left outside of what they can cover. They'll focus on bacteria and viruses, but some of the bacteria, funguses and other growths are not going to be effectively disinfected, primarily because the disinfectant can't get in to that, that fungus that is growing. It can affect the surface, but won't get right inside it. For the rest of it, it's all about risk assessment. And, I've kind of explained that well enough for you, but we will have a look at, is it human compatible? So if we're going to get people exposed to this, is it human safe? Is it not human safe? It's not whether you can or can't use it. It will then just define your exposure to people. So we do use pretty miserable things inside our chambers, like bleach, like jick, as we might call it. I have to change my word from jick to bleach because they know what I'm talking about around here. Does it have a smell? And I apologize for the smelling of odor. That was the spell checker that did that. It's not how you spell the word. But what we want to make sure is that any residual odor afterwards is acceptable. Again, using sodium hypochlorite or bleach has a very unpleasant smell afterwards. And the safety data sheet will indicate what should happen after cleaning, flushing, and drying, what the residual parts per million levels are. The problem with us humans is that some of these substances we are very sensitive to in very, very low ppm. So sulfur, one of the sulfates, not sulfur dioxide, I forget which one it is now, but hydrogen sulfide, we are sensitive to 0.5 of a part per million or 500 parts per billion we can actually pick up with our noses. Staff health and safety, so the people that are going to be doing the disinfection, what are their risks and what PPE do they need to be considering. So his point is buying something that is too hazardous to actually apply. Using a gas or something else is too hazardous in most applications unless you have a very specifically designed disinfectant room or location. It's not something that's practical. Is the residue left behind non-toxic and non-flammable? So if we touch it, is it going to be non-toxic? And there's always going to be a residue. We just need to know what it is and what its safety level is. Our unique environment is high levels of oxygen. Multi-place chamber, less so because we keep it below 23.5%. But in a multi-place chamber, if there is any residue, anything above 25% is defined as oxygen enriched. And we need to check with the NFPA and the American Society for Testing Materials, ASTM, whether it's going to be safe for use in an oxygen environment or not. And let me just say, alcohol is a great disinfectant, and it is used. And it's certainly not compatible to an oxygen-enriched environment. So we need to make sure that once it's been cleaned, that it's properly dry and then no residual vapors. Then during application, this is a real concern to us. So using alcohol in a confined space, any form of a spark is going to cause a fire to occur. So we need to know that to be able to ventilate properly or exclude people, exclude heat sources. Then post-application, if there are any residual vapors afterwards, some things take a long time to actually dry out, and it will require thorough flushing. And I know most of us don't do that. We wipe the insides of our chambers down or the insides of our helmets down, and then we don't flush it off afterwards. And some of these disinfectants require flushing and require enforced drying to make sure that there are no flammable vapors left. One of our big questions is it compatible with our acrylics and with our seals and the metals we're using? Again, bleach is very corrosive and will cause or exposed steel surfaces to corrode. So if we're going to use it, we need to be very careful and obviously flush and dry afterwards on any exposed steel surfaces. Okay, then you need to look at the application. Is it something that's practical? And if we have to soak something, there's no point trying to soak a chamber, so that's not really going to work very well. And then how long does it take afterwards to dry? These are practicalities for us to consider. How easy is it to put on? Again, do we have to spray it on? In which case, we need to make sure we have proper PPE and the proper equipment. So application is important. Then waste disposal afterwards. The safety data sheet will tell you that you either have to dispose it, you can pour it down the drain into the sink, or you've got to contain it and use proper waste disposal. Then we come to the obvious one. So you might find a great disinfectant that's available in Europe or in the US, but it's just not available in South Africa and it's not allowed to be imported. So those are some of the constraints. Here in the US, California is incredibly strict when it comes to disinfectants, and so often I've been giving guidance to scuba divers through Dan. In fact, I've got a little team and we sit down and we go through these disinfectants and we find things like one that is good for wetsuits, only to find that you cannot use it in California. And then at the end of the day, let's be realistic. It's all about the price. And some disinfectants are relatively inexpensive, but they are highly diluted. So we're not going to get as much out of it. And we need to bear that in mind. You might get a very concentrated disinfectant that you can do the mixing and you can optimize on the mixing, so it becomes less expensive over the full volume of concentrate that you're using, and other ones are pre-diluted and they might be too strong. And of course, they're going to affect the price. So those are the 14 criteria that when you ask me the question, I normally sigh and say, okay, let's go back and have a look and see what we know in terms of the safety data sheet, and I will then be looking at the EPA and other places for guidance on that. As a general rule, the quaternary ammonium products, or quats as we call them, are very effective against most pesticides, most pathogens, and certainly with SARS-CoV-2. The trick with it is it needs proper disposal, so you can't just flush it away or pour it onto the floor as you can do with many of the other disinfectants. Then that's kind of the common one we see in hyperbaric environments, but it's not the only active ingredient. And so many of the disinfectants we come across have other active ingredients, and citric acid is a great one, by the way. And another one is thiamyl, which is what we call Listerine. I'll come to those in a moment. But one would take that disinfectant, look at the active components and then see whether those are compatible with our hyperbaric environment. And PVHO2, which is the in-service guidelines for a hyperbaric chamber, has an Appendix 5 that lists many of the harmful ingredients to acrylic windows. Same with ammonia-based cleaners, citric acid I mentioned, which is a very strong viricide. People come up with iodine-based disinfectants, but those are antiseptics. They're meant for disinfecting wounds and stuff, not surfaces. And I know some people want to use them for that, but that's not what they're designed or intended for. Hydrogen peroxide is a question asked fairly frequently. We've had to answer this one. And the EPA has a relatively low concentration required, so between 0.5 and 3%, and the PVHO2 limits it to 20%. So peroxide in terms of acrylic materials is relatively safe, but that's not the same for seals and other surfaces that will degrade with too much peroxide, but very effective. Harmful, but very effective. Phenolic compounds, again, one has to check the concentrations in PVHO2. And then thiamine, which is, Listerine's quite a common disinfectant around here. And of course, the question was thrown back at it's actually very, very effective pesticide in many of the aspects we're dealing with. So it's almost a natural-based product rather than a chemical-based product. Then we have our alcohol-based products, which are, very, very effective. Problem is that for acrylic windows, it has to be less than 4% by volume. In terms of flammability, isopropyl alcohol needs to be at least 20%, okay? That's not talking about the vapor, though. It's 20% in the actual alcohol itself to be considered a flammable mixture, but only at 890 Fahrenheit. Excuse me for using that. I try to clean up all the other things. I'm so ingrained in thinking imperial here. And in terms of list N, which is the EPA's categorization, they say anywhere between 20 and 60% is effective. So we're out of the range of it is flammable. It's not safe for acrylics. So acrylic-based products, if we're going to use them, we need to be really, really careful. And then we come down to bleach, to our JIC, as we would call it, sodium hypochlorite. The CDC say that anything above 2%. Now remember, when we buy product, there's only 5% of that bleach of the JIC that is active. The rest of it is solution. So it's 5% of 2%, which is about 1,000 parts per million. So that's the concentration required, which is actually less than you might think. We tend to use more than that. And we've had to correct many of the manufacturers of equipment saying you need to use 10%. It's way, way, way beyond where it needs to be. It's on the EPA list N, which means approved for use to disinfect COVID. And PVHO allows up to 15%. Or 7,500 ppm, so definitely in hyperbaric chambers, not just acrylics, but everything else that's safe for use. And if we flush it correctly, the bleach, then we will reduce it to below 20 ppm, and that's actually acceptable. And we did some in-house experiments, and one of the dive operators around here did experiments with demand valves, and after flushing it properly, letting it dry naturally, so hanging up to dry the next morning, absolutely no trace of any bleach. So in our hyperbaric facilities with our masks, if we don't overdo the solution and we flush it properly and let it dry naturally, you should not have any residual JIC. But of course, in the pores of the breathing apparatus, we need to make sure that we get inside there. And so it works great with hoods. Some of the masks a little less effectively, but it should work effectively. And then just the last point, that most of the existing disinfectant, virus disinfection products appear to be effective to kill the COVID virus, but only for hard or non-porous surfaces. The porous surfaces, it does not yet, because it doesn't kill other viruses effectively, and so one would assume the same would hold for COVID-2, but it will certainly reduce the quantity and thereby limiting the loading of virus that the person might get as a result of contact. And of course, we know that contact has become less of an issue. It's now mostly airborne stuff that one's concerned about. Let me show you what we've learned in the last year and a half since being faced with this. So the EPA has so-called List N. It's just a subset of EPA, but List N contains the disinfectants that, where the manufacturers apply to the EPA, not based on testing. That's the interesting thing. It's based on compatible or comparative viruses. It then appears on list N. So if your disinfectant, doesn't matter where you are in the world, if your disinfectant is on list N, then you know at least the EPA in the USA has approved it. And I can tell you that there are products, I think I worked with Jonathan on this one, I can't remember, but the product that was proposed had an EPA registration number, and I could go back and see what it actually said. There's more to it just than what's on list N. I'll come to that in a moment. It identifies the active ingredient. It then tells you which manufacturer or supplier or agent has applied for permission to have it registered. And then it gives you the directions to follow, and it says, treat this as if it was a feline virus or was any other human virus. It tells you, because it's not going to say COVID-2, it's going to tell you other types of viruses, and you're going to apply it in the same way. And on list N means it's rated as an effective disinfectant against COVID virus. There's if you quick enough, there's a QR code for you, but I'm actually going to go up here and I'm going to try my luck again. It sometimes works, sometimes not. So if I click on list N, it should take me to, okay, but you're not going to see that, so I'll need to put it over here, I guess. So that's what it looks like, that particular tool. You click launch, and in that, you're going to put in the EPA number, and if you look at the registration number there, these happen to be quats. You can see that's the company that applied. That's the directions. You're going to follow directions for this particular virus. It is dilutable, so it comes sold in concentrated form, but hard, non-porous surfaces, and that'll tell you it kills harder to kill pathogens than SARS-CoV-2. So we're happy with that. I need to now close this down. I think I can move it away. So we're going to come back to that in a moment. Okay, just tell me if I'm talking here and you're not seeing stuff on the screen, but that was meant to show you how you get into the EPA database to see whether it's on list N, meaning whether it's rated by the EPA as suitable to kill the virus we're concerned about, or any of the other viruses, because in that list you're still going to see them too. And you can use the EPA registration number, the active ingredient. Those are two ways to actually search in that particular website. Very powerful. And with time, we've actually got to know most of the people on the EPA that do this registration, and been able to talk to them about various scuba and commercial diving related applications. Because it's easy to say the disinfectant is suitable. The question is it going to work in our particular environment with the materials we're using? Now, you have your EPA registration number either by putting in getting it from the data sheet or from your search through the web elsewhere. But you'll have an EPA registration number, and I'm going to show you how valuable this number really is to us. So using that number, or you can still search on brand, on product name, on active ingredients, and then you get this thing called the CAS number. Let me just minimize this over here, which is, I think most of us know, it's the Chemical Abstract Service Number, or the PC code, which is the Pesticide Chemical Code. Those are names very often printed. So you'll see this name and not the EPA registration number. But you can put this number into the search engine, which looks like that. And from that, you can get really great information. It's the full application made by the manufacturer to the EPA to be classified as an EPA registered product, not necessarily for COVID. And that document will tell you what pathogens it can kill, what it's made of, what sort of surfaces, what materials it's effective to be used against, and then obviously how to apply it per different type of pathogen. So one product might have different applications for different types of pathogens. Usually it's about the resistance or resilience of that pathogen to that disinfectant. I use the word materials here because we don't find that magic word hyperbaric, but we can find breathing apparatus, full face masks, and various other things that we can then transpose to our hyperbaric equipment. So if I click on this particular page and I go to search any type of product, I can actually put the EPA number in there. No, thank you. I can put the EPA number inside here, and it will then take me to whatever that particular product is. And it's normally about a 5 to 20 page document. And as I say, you'll get the active ingredients, which allows you to go back to PVHO and check that it's compatible for our hyperbaric environment. And then we need to interpret what materials is it good for dealing with mattresses, hospital application. That's really a great one to use. But often those are not on list N, so we have to kind of do a fair amount of looking to get to where we want to get to. Sorry, I didn't show you this particular page. So I have to remember that you can't always see what I can see. So this is where that QR code takes you to, and this is a pesticide website, and you click on there for any type of product. I can't think offhand. We could put in here peroxide maybe and see if it'll tell us, well, the peroxide, and click that or search on that, and it should come up with all sorts of different peroxide approved products. So let's take this benzoyl peroxide, the first one. It goes searching and it came up blank. So I don't know why it comes up blank. Let me see if I can go back one, take another one, or in fact, let me take it should actually, if you click on here, it should come up. Here we go. So there's that particular application, and there's their registration number, and you get all the data from this that you're required to do your search and decide whether the product is suitable. So there is their last application. It's a PDF file, and from that you see where they applied to the EPA, when they applied, and it's really excellent information on the ingredients, on the pesticides, the surfaces, and what you need to do before the time. So this one here says thoroughly clean all surfaces with soap or detergent and rinse with water before you start with the pesticide. And then it'll go through different types of surfaces. So this one happens to be a washing room. But remember, the EPA is a registration of all pesticides. We're going to be looking for the ones specifically compatible or useful for our application. So that's just some of the tools that we have out there. And this is not just for COVID. We can find everything that we're concerned about. So new viruses, new bacteria that come up in the future, this is where you'd go to look to see whether they're effective. Okay, 3 other questions we've been asked. And the first one is, can we use UV disinfection in a hyperbaric facility? And I'm going to share with you that I'm a little at odds with some of my colleagues on this one in the hyperbaric context. But let's just look at UV disinfection. The EPA accept the method, but not the devices that are used. So they will agree to the wavelength and the length of time and so on, but they don't endorse devices, and we normally want to go and buy a particular device. The CDC accepts this, but obviously with some caveats, and there are good reasons for those. It's an incredibly powerful disinfectant if it's applied correctly, and the problem is practical application is the issue. Of course, it's effective. We're concerned about things on the surface, but it is also used in airborne ventilation ducts. So in the hospital, they would be very effective if you were concerned in your hyperbaric room. You put in a UV lamp up in the air intake, and you can kill everything that goes before it actually gets to the filters, or if you want to, after the filters. So very effective, just has a very limited life. So every year, you'll be replacing your UV lamps. It leaves no residue. So we don't have any concerns about that. Here's the catch with UV disinfection. So it depends on the distance. So it's inversely proportional to the square of the distance from the source, which means that if you have surfaces at distances from each other, you have to get enough irradiation to get to the furthest area, which means that you're going to then fry the parts that are closer to the source. So in that particular case, it's really focused or designed for surfaces that are relatively similar in distance from the actual lamp or the source of UV. And it's difficult then to get to all of your surfaces. Its optimum wavelength is 254 nanometers, actually very, very specific area where it's most effective. And here, I'm not going to give you UV 101, but UV light is defined as light in the wavelength, the range between 400 nanometers and actually 10 nanometers, but that's outer space, so we don't deal with 10 things below 100. And we divide it up into UVA, which is what we would get exposed to by the sun, UVB, which is normally going to come from a source of some sort, and UVC, which is highly dangerous. We can tolerate small amounts of UVB, but you will cause cataract growth and damage to people in UVB. So we only allow people to see UVA, and fortunately, the B and the C are mostly screened out by the ozone layer, by the upper atmosphere. Because it is absorbed by surfaces, UVA can reflect, but UVB and UVC don't reflect. Very important thing to know. This magic number, 320, I'm going to come to that number in a moment because that's applicable to us. Okay, you can argue as much as you want to with me now. You can see where 254 nanometers fits in UVC. UVA is highly reflective. So we know that sun on the snow, that's why we have to use those dark glasses when we're snow skiing. Up to 80% of the incoming UV is reflected. UVC does not reflect at all. And, I get told when you see behind corners, it cannot see behind corners. And when you look at the research, they do the research on the surface that the UV gets to, and then they test other surfaces, but those aren't surfaces that would be typically contaminated. And I've had this discussion with them, and we have to agree to disagree. But because they didn't then go and physically contaminate the underside of the seat. So it's effective when it hits something, not effective when it can't see something. So not ideal for shadow areas. And it is most effective, again, when we get rid of the gross contamination. Otherwise, it only affects the surface of that contaminant, and the UVC is absorbed by that surface. Of course, there are cautions. First caution. To be effective, the UV has to be at 254 nanometers, very clearly in the UVC category, and we know that your window will become damaged anything below 320 nanometers. So it's only safe for above that, which will kill other bugs, but will not kill the SARS-CoV-2 virus. So if it's going to be used, it can be used on very specific surfaces in a hyperbaric environment. It cannot be used on acrylics. So if you use it in a multiplex chamber, you need to screen your acrylic windows, and you need to realize it's not going to kill anything in the bilge or anything in the underside of surfaces. I don't believe it has application except if you're really concerned about a focused area in the hyperbaric chamber, and you can focus the UV light on that. It does degrade plastics as well as causing crazing in acrylics. So not human safe. You have to isolate the area, and it requires a fairly lengthy period of time, typically 15 to 30 minutes, depending on the intensity, and that's not ideal if you have patients going through your chamber. So again, it's easily blocked by most materials. It's absorbed certainly at that wavelength, not effective in areas where it can't get direct line of sight, and not effective for funguses and bacteria. Great for viruses. And if the virus is your concern, then it's certainly something that can be used. And just for those of you that might be interested in pursuing this, there are a whole bunch of references that I've kind of built up. These are the most important ones. And number 2 and number 6, they're just alphabetical, are studies done specifically in hyperbaric environments. And certainly in the first one, it was published. I didn't get a chance to review the paper. I often get these papers to review. And I went back and we had our discussion with Dr. Moon and other very famous people there, and they agreed that they were looking at a particular surface that they were concerned about. In fact, they were just experimenting with the manufacturer to ask them to test it. There were 2 different devices. One was effective, the other not. But they primarily looked at one surface area that they contaminated and then checked afterwards. Let me go back one, because you can see here they're aiming at reducing the bacterial load, not killing it, just reducing the load. Great for viruses, less effective for bacteria. Here's another one that gets thrown at us, and I've had these questions from all over, hyperbaric folks, diving people, commercial diving people. The magic word about, or the magic concept about ozone is that when you have these CPAP machines and home oxygen concentrators, the instructions, they'll give you a little box and they say, put your mask in this box. It's ozone. It will kill all the bugs. And that's the way you do it. Okay, fair enough. In terms of a disinfectant, it's not EPA endorsed for surfaces. So that's number 1. No matter what the manufacturer tells you, the manufacturer is actually referring to sanitization, but using the term disinfection. And they get reported to the EPA, and the EPA then, talk to them and say, you cannot market this as a disinfectant. Great for wastewater treatment. So it does have its applications in solution. And the FDA has not cleared it for masks. So we really can't be using ozone in our facilities. I won't go into the theory. I just want to show you out of interest that ozone is produced in the 185 nanometer range of ultraviolet light. So it's produced by ultraviolet light, but it's destroyed in the area where we're using UV as a disinfectant, just kind of as a matter of interest where it fits. So very much in the UVC range to produce the ozone. You need significant amounts to actually achieve the disinfection, but it's highly toxic, and so it's got to be contained. So you have to put it in a case of some sort, seal that off, do the right exposure time to make sure that you disinfect the surfaces and have no leakage because it's not going to be great for, especially for vulnerable patients. It appears to be effective as a sanitizer for soft materials, and one could use it for your hoods and for your masks. It does degrade them with time, but in the lifespan of the equipment we're using in a hyperbaric facility, this is not that significant. But it's not great for O-rings and seals. So if you were doing ozone disinfectant for your masks or hoods, or your parts of your diving, your commercial diving equipment that goes into the patient, into the diver's mouth, that's fine. By the time, that mask is degraded naturally, you wouldn't really be concerned about the ozone exposure, but you would then remove the O-rings and seals, especially nitrile. You need to remove it from that before you then disinfect it. Okay, here's a question that is asked and that kind of came back to me, and I'll share with you that I had a really interesting debate with a compressor manufacturer. I'll keep that to the last part of this slide. So, you know that we talk about airborne transmission. So what about the ventilation system in the building? Can we get transmission through the filters and stuff? We use HEPA filters, and there are a whole bunch of different things that we look at. So in terms of particles in general, we know that a virus will be as small as 0.1 of a micron. Particles are typically defined as anything around bigger than 0.3 micron, and droplets are going to be around 5 microns. So if we were concerned about droplets, they're relatively easy to filter. If we're concerned about virus particles specific, then we need to have something that can deal with 0.1 of a micron. The SARS-CoV-2 fits between 0.16 and 0.6 of a micron. So if you forget about the droplet form and you look at the virus, that's the range of that particular size. And so we get told HEPA filters are the answer, and they really are. They're very effective against this, but only 99.97% effective. So your virus loading is incredibly low, but we'll still get through the HEPA filter, but we want to know the science behind it. And so we can see that it's 4 nines at less than 0.05 of a micron. At 0.2, it drops down to 99.94, but it's rated at 0.3 microns, so it's focused on the 0.3 micron range, and here it's going to be 99.97% effective. But you can see the effectiveness dips around this area. I can't tell you why, and then it goes back up to 4 nines, so very, very effective. So our SARS-CoV-2 virus sits in that range there, so there are going to be virus particles that are not going to be affected, but 3 nines, 99.94. They measure these in log scales usually, and they'll talk about a log 2 to a log 6. It just means the number of nines at the end of the day. So you can see where the SARS-CoV-2 virus actually fits in. However, that's fine for the ventilation system in the hospital. When we get inside our chamber, if we were to have contamination in our breathing gas coming into the chamber, we obviously increase the number of particles with depth. And we know that from carbon dioxide and from other things, it's that surface equivalent value, that you've got to relate this to what is allowed at the surface, because when you multiply that, when you go down to depth, it's going to multiply by the number of atmospheres. So, at 1 atmosphere, 1,000 parts per million of something will basically equate to 6,000 parts per million at 6 atmospheres, because the number of molecules increases. So we would get 2.8 times the number of virus particles at a typical table 6 or 2.8 ATA treatment. But now where's it going to come from in terms of our diving system? So we have an air compressor. Hopefully our intake to the compressor is controlled, and you won't have somebody coughing or sputtering or contaminating the intake. So that's relatively easy to control, assuming somehow it gets through. There's an inlet filter that they claim is good for anything above 5 microns. It's actually better than that. We've seen that from inlets to diving regulators. It actually gets rid of things down to about 1 micron, but it's not guaranteed. Then we have our adiabatic heating, that heat of compression when we compress a gas. And the minimum adiabatic heating is about 260 degrees Celsius. And we know that 60 degrees Celsius will start to kill the virus, but you require 30 minutes of time. But at 260 degrees, the time span to kill the virus is very short. So especially in a high-pressure compressor, I can't see this surviving 3 or 4 stages of compression. Then you have the moisture traps, where the virus is likely to attach itself to the moisture or the oil particles and drop out. So your moisture trap your waste material from your interstage straps could be contaminated. And then you've got the final breathing air filter system, and that should be down at about minus 45 degrees Celsius. So any droplets would have fallen out long before they come out of the breathing air filter. Standard breathing air filters in terms of particulates are rated for 5 microns and above. But we don't get that. We typically get almost no particles coming through if the filter itself is actually changed and run within its operating time span. Low pressure filters, using what we call oil-free air, medical grade air, they claim to have nothing larger than 0.1 of a micron, and that's the ISO scale, the class of filter that we use. And we would be using a class of filter where nothing larger than 0.1 micron should get through, meaning we know that the SARS-CoV-2 virus is 0.16, should be good to get through. But there was work done by, I just want to close the screen down here so that I can see what I'm doing, by the British Compressed Air Society, and it was done last year after COVID struck, and they could measure no evidence of transmission of the virus. Anyway, armed with all this information, Bauer, I shouldn't actually mention Bauer, but they're very proud of their B virus, I think it's called. It's an ultraviolet source that they put before the air goes into the compressor that will kill all virus particles before it enters the compressor. I won't go into the technical discussion with them because I had some doubts because of the dwell time, the time that the particle is going to spend in that chamber. But the point I was trying to make is that whether or not you kill the virus before it goes in, it's not going to come out the other side. And anyway, they sent it off to a laboratory to be tested, and the laboratory came back with a scientific explanation. They didn't actually pass a virus through. They just worked on the science and the UV exposure and everything else. And so we don't really know. But what we do know is that particles that have entered the compressor that the British did some work on, there was no evidence that came out the other side. No evidence in terms of what we know at the moment. And then, of course, and we won't go into this debate now, is this a concern in terms of airborne particles or in terms of transmission by droplets? And I don't think that has been satisfactorily answered yet, but in terms of droplet transmission, there's no ways those droplets will make their way through a compressor. Then lastly, one of the new techniques that we've been asked to evaluate is what they call fogging or misting or electrostatic disinfection. It's a pretty neat technique. It's not allowed by the EPA because the EPA only really talks about surface contact in liquid form. So you can spray it on that it gets wet, you can wipe it down, or you can soak it. And they refute the claim that it's the disinfectant. They say it's only a sanitizer. I won't pass my comment until I get to the end of this. It's a great 4D application, meaning all 4 dimensions, 3 contact dimensions, and then airborne. So the 4th dimension means it's in the air, but we can actually effectively disinfect. You'd use exactly the same process that you'd select for any disinfectant in terms of what's left behind, compatibility, and so on. Obviously, people with compromised respiratory issues, it's not suitable for them, or it's not that it isn't suitable, but you need to make sure that before they get exposed, that all of that fogging agent has been removed. And it works on airborne, porous, and non-porous surfaces. Now, the only discussion I'd have with that is how effective is it between those 3 different categories. So most of it is what they call fogging or misting, and that theoretically is able to get into relatively inaccessible areas like the weave of materials or of a wetsuit. I keep coming back to wetsuit because that's a great example of a surface, whether it's a mattress covering or a wetsuit, any neoprene-based material is a good example of things that are difficult to clean. The process we use, though, is basically affected by gravity. So when you spray it, it's going to tend to fall down to the ground, which means it's going to have uneven surface contact. So you get overexposed areas, not that it's a problem, but you'll get underexposed areas. Whereas electrostatic fogging, so it's basically charging those fogging particles, earthing your chamber, for example, and it will wrap around. It'll go into all sorts of crevices and so on, and spreads very, very evenly. So the electrostatic version of this fogging technique is really good. But I'm going to flip up the next prompt for you and you'll see. You get to select the disinfectant. So this is just an application technique. You need to select the disinfectant, and the best disinfectant to be used is sodium hypochlorite, bleach, check. And we know that it is not that effective in terms of non-porous materials, but it does serve as a very, very effective disinfectant. And it is likely to get into those weaves, those pores, but very, very tough to get them out again. So you don't really want to be washing things as a disinfectant in things that are really difficult to then get any remaining disinfectant out from. Okay, let me just kind of get to the end of this by saying we've done all our homework, we know what it is we want to use, and now we need to turn this into something that we can apply. So we'll start off by putting together a procedure. That's where we'll do the homework to see what materials it is effective against, what sort of cleaning are we going to be achieving? Is it just cleaning? Is it disinfection? Is it a combination of them? This will all be part of your procedure. Selection of the actual disinfectant, either the chemical or the process. And to select that, obviously we're going to go through that whole selection process. And then we need to test it to make sure that it is actually effective. And in a hospital setting, you typically take a contaminated area, apply the disinfection, take a swab, send it away to the lab, and make sure that it is actually achieving the goal. Part of the process or the procedure will be determining how to make sure that staff are kept safe, that there's no, hazard to them when they're actually applying it. Then they need to be trained in how to apply it effectively, and obviously that they need to be trained in terms of what PPE to use and how much exposure and how much ventilation afterwards. Then the real trick with any process that you put in place is to make sure that people do it consistently. And so often this is where things break down because people are very, very attentive in the beginning, and with time they then start to cut corners, I'm not going to wait exactly 15 minutes, it'll become 14 minutes, becomes 13 minutes. Once you break the procedure, then, you've really lost control. And ultimately maintain your records. So obviously you keep a procedure and you'd keep the qualification of the procedure when it was set for testing. But also after each disinfection, in a hyperbaric context, you put that into your operating log that we disinfected following this particular procedure. And keep that because, again, that gives the doctor confidence that the staff are taking care of the equipment, and if something does get spread, then, and they blame the hyperbaric facility, say, here's our procedure, it is effective, it was done, here are the records, you can point holes in and say, well, was the operator lying or not? But that's a completely different part of any legal process to go through. So basically, again, infection control 101. And then as my final note to this, I just really want to summarize that from everything that we've learned, research, experience, and current practices, both and looking at the EPA registration and the advice from the Center for Disease Control, we can see that our existing products and methods for all sorts of other known pathogens are effective in inactivating the SARS virus strains because they are not resilient strains. And all we want to have at the end of the day is consistency, compliance with the process, the procedure, and we can make sure that we're not going to get surface transmitted COVID-2, and if we are spraying it or if we are using UV in the air supply, we're not going to be getting airborne particles that are going to be coming through. So while we've been getting all these questions about is it effective, what we can tell them is that it's accepted and registered as being effective, but if it can kill other virus particles, ones that are more resilient than COVID-2, then yes, it is going to be effective as long as you follow the processes and as long as it's compatible with what it is that you're doing. So you don't want to destroy your materials or leave residue or make it unsafe for people afterwards. And then just lastly, a bunch of the resources that I found really, really useful in terms of researching most of the stuff. So if you looked at the airborne, looked at the UV, they were separate references, ozone potential, and a lot of them done very specifically for either the coronaviruses, because SARS-CoV-2 is only one of those viruses, and then looking at underwater breathing apparatus manuals. We've got our Kirby Morgan and the US Navy and other people already have technical instructions. Some of the dive equipment manufacturers have technical instructions for disinfection. And as long as in the instructions you see that disinfectant has been applied correctly and it's suitable for other viruses, then you can have peace of mind that it's going to be effective for your SARS-CoV-2. You just want to make sure that you've done the homework and that you've made sure that it's been done compliantly and that records have been kept. So that's really what I wanted to share with you folks. I want to try and get out of here now. Stop share and turn on the video and hand it back to Cecilia. So any questions you have?
Wow. Thank you very much, Francois. I can see that there was a lot of research, a lot of work, a lot of effort, and a lot of time that went into that. And obviously it's still ongoing with a lot of it. So thank you very, very much. A very lengthy discussion on a very important topic for all of us in not only the diving and hyperbaric medicine setting, but I think in any other clinical setting as well. The floor is now open for questions. If there are any of the delegates here in person or online that would like to ask Francois a question, please raise your hand or just start talking, and you're more than welcome.
I think my pass or fail in my talk is Jack, whether Jack has got any tomatoes he wants to throw at me. I see Jonathan has a question. You just need to unmute, Joe. There we go.
Yes, hello, Francois. How are you?
I'm well, thank you.
A couple of questions. The one was just related to the purification of really the breathing air, the pre-compressor air, and in fact even the environmental air of the facility where the chamber is located. I mean, I think Jack spoke to that issue a little bit earlier in terms of replacement times, etc., of how many air replacements are required. But I was wondering if either of you being Francois and Jack, have any knowledge of the plasma technology that's being produced in commercial models by companies like Daikin, where you basically have two highly charged plates and the air travels between it, and the theory is that electrons pass between the two, oxidize oxygen. According to them, 99.7% of viruses and pollen particles and so on essentially get vaporized. Seems like a logical idea, but do either of you have any verification knowledge around those principles?
So from my side, I don't know if Jack is there, but from my side, yes, it is a very effective process. The problem is it's relatively limited to the airflow. So obviously there's a restricted amount of air you can put through based on the size, obviously, of the plasma generator. We see it applied in our home air conditioning units, certainly the split units. They've got a little button you can push that then they call it ionizes the air and destroys particles. It doesn't remove all the particles because you can still smell dust. So it is very effective. I would surmise that it would kill any virus particles coming through, as long as it is designed correctly and matched to the demand that you have. But you would be talking now about hospital air, or the air in a particular, let's say in a ward where you have people that are contaminated or people that are infected breathing out, and you want to scrub out those particles, and you have like seven air changes per hour, whatever they decide it's going to be. From my side, I see no reason why it wouldn't be effective. I haven't seen research done on it, JR, in terms of the SARS-CoV-2 virus, but if research has been done on other viruses that are more resilient, then one would conclude from that it certainly would be. And if used in conjunction with a HEPA filter, I would say it would be highly effective.
Yeah.
If Jack
But I guess more expensive than, just simply replacing the air by dilution.
Yeah, so my comment would be that that is exactly what it's about, So if you want to deal with large volumes of air, it's going to be problematic because there's obviously a dwell time that is an issue. It's the same with UVGI, so ultraviolet irradiation of air. Where you essentially need to have what you're essentially doing is that you give the viruses and the bacteria, if you talk about TB and things like that, you give them sunburn until they die, if you want to look at it in that manner. So you irradiate them essentially. And as you know, for you to get sunburn, you need to dwell a certain time, and therefore you would reduce the amount of ventilation in order to make it more effective. And if you look at the overall efficacy of increasing ventilation, that would typically what we would normally go for. So we would normally say don't waste a lot of money on these sort of technologies, rather use something that increase the ventilation and dilute the allergens and things like that. It's obviously not applicable if you work with a highly infectious agent, so if you work with, let's say, aerosol producing procedures in an Ebola ward in Tygerberg Hospital, for instance, and some procedures that you do in theater. So there you would definitely go for something like a HEPA filter or something like that. But again, we don't go for the UVGI and those sort of things. The maintenance issues, there's a lot of other issues that come into play as well. So, so that would be my opinion on those issues.
If I can add to that, you would need to look at the log scale of efficacy. And as Jack said, it's the dwell time. And that was my big thing with Bauer. I didn't believe they had enough dwell time to effectively kill it. So you'd have to have a very strong radiation source, a UV source up in the roof where the ventilator is, the ventilation ducts on. You need to slow the duct down, the flow down, to get that dwell time. Or if you keep it at the normal speed, you're going to end up with maybe 95% of the pathogens being killed. Hopefully the rest will be caught in the HEPA filters, but correctly you want to try and speed up the air changes, because otherwise you've got dwell time of the virus in the room. So it's not only up in the duct but also in the room. You want to get those viruses up to the HEPA filters as fast as you can. And HEPA filters, they're also used in conjunction with UV. But remember that UV light lasts about a year, and then there's a rapid decline in its effectiveness. So you'll be constantly getting people up into the ducting to replace them.
Part of my thinking in terms of essentially the plasma principle for eliminating pathogens wouldn't probably really be applicable in South Africa, but I was thinking in the Northern Hemisphere, where you have a -20, odd centigrade outside temperature, it becomes very challenging to replace the volume of the air in a room rapidly, and then something like a plasma system might make more sense financially anyway.
Do you mean -20 outside is a problem with heat, having to heat the air? Is that what you're concerned with? Well, I'm saying
if you're wanting to replace the volume in that room 15 to 20 times an hour, and with fresh, air sourced from the external environment.
That's very rare, Jonathan. Most of these systems have got a recirculating, and then they allow a small degree of fresh air to come in to make up for the metabolically consumed oxygen. But most of them will have a fairly small amount of fresh air they're drawing in. It's mostly going to be recirculating. And in cold places like where we are here, they actually dampen down even further so that you don't... you maintain the heat. You certainly don't bring in fresh air from outside.
No, exactly. So that's my point, is that in those kind of environments, I would imagine air purification in terms of plasma or UV makes more sense than in Africa, where we just have, can just suck from the blue sky.
Sure. Anything else?
Yeah, can I add something from the UK? First of all, it's great to hear you again. It's Phil here.
Yes, hi, Phil.
As usual, you wonderful talk and great research, etc., etc. Just you haven't changed. Fantastic. In the commercial diving world, of course, we have an interesting concept in saturation, in that we have something called helium reclaim. And that means that in a month, you're going to be reusing a lot of the helium again and again and again and again. So, of course, if you take a virus particle in there, if you're not careful and you don't have systems in place, then it'll just go round and round and round and round, and everyone loves you, and you share everything beautifully. So what we've used currently, and it may be wrong, but we currently basically use either Vercom as a disinfectant or Trigene, and we try and alternate them, or Chemgene. We try and alternate them. But also the filters on the helium reclaim system and the SAT systems as a whole go down to 0.01 microns. So that tends to help significantly, in that there's not much that gets through them. It's certainly not perfect, but so far it seems to be doing the job quite well, and helium reclaim systems have not caused any major issues so far.
Well, I would say if it's 0.01 micron, then there are no ways that there are any virus particles that are going back. I don't know what is smaller than that. There are some things that are smaller, but certainly in terms of SARS-CoV-2, there's no ways it's going to be able to get there. Your only concern then would be surface contact, and we know that you test the divers anyway. And so as good as the testing is, it's very unlikely you're going to get that sort of level of contamination inside the hyperbaric environment. It's mostly, as you know, to do with bacteria and rotten feet and stuff from bacteria that you can't filter out in terms of it's not part of your circulating reclaim system or regen system. Sorry, regen for the SAT system and reclaim for the gas that's being exhaled by the diver. So yeah, that's interesting.
Yeah, it's great. It's lovely to hear you talk, and absolutely right. It's a unique environment that these guys live and work in.
Anything else?
Any other questions from the floor or from the platform? Any other comments? It doesn't look like it. Okay. Francois, thank you very much.
Oh, you're welcome.
I think it was a fantastic session, fantastic talk. Okay, I think is there anybody that wants a leg stretch, quickly go and grab a coffee,